what I'm going to do today is go ahead and finish section 8.2 today. I'll try to finish 8.2 today. All right. In this set, well, we've already talked about measures of center. Okay. Measures of center deals with things like the mean, the median, and the mode. And of course, the mean is the average of the data values that you have. You just take the sum of your data values and divide by the number of data values that are given. Give a few examples of those. Then we talk about the median, which is the middle number. Anytime you're finding the median, you have to sort your data value, your data set in numerical order from least to greatest and take the middle number. Usually, if you have an odd number of data values, the middle number will automatically be the mean. But an even number of data values, you have to take the average of the two middle numbers. Okay. And then the mode is the most frequent data value in that particular set. Okay. And we talked about that. Also, we talked about the stem and leaf plot, how to construct the stem and leaf plot. Okay, so here pretty much the first number usually would be the stem, the last digit in each data set would be your leaves. Okay, and also I forgot to mention that when you do a stem and leaf plot, you're also doing something called a histogram. Because if you take that stem and leaf plot that we did on Wednesday, and this is the one that we did. By the way, let me go ahead and backtrack on this one here, because this was the stem and leaf plot that we did last class. Okay, and this is what we came up with. Now, if you were to take this stem and leaf plot that I have here, and you tilt it on a side, it's going to be somewhat like a histogram, okay? Because in a histogram, you're going to be dealing with quantitative data values. For the first one, between 50 and 59, the second one, between 60 and 69, then 70 to 79, and then 80 to 89, okay? So that's pretty much similar to a histogram, okay? All right, any questions on that? Okay, forgot to bring that up on last class meeting, but thought I'd bring that up now. Okay. All right, so now we're gonna pick up with a dot plot, or sometimes it's called a line plot. Okay, a dot plot is also called a line plot. That's going to be a graph for numerical variables where individual values are plotted as dots or other symbols, such as, let's say, lowercase x. Okay. So if we had something like this, the data shows the prices of various models of inkjet printers. Make a dot plot for the data. So here's the data set right here. And we want to make a dot plot for that, okay? So on the next slide, well, here shows the prices and their frequencies. Okay, so the horizontal line represents the cost in dollars. And of course, those dots represent each of the individual prices. And sometimes, you know, those dots also represent frequencies as well. Like, as you can see,
You lose some of the data that way on like the stem leaf plot.
Yeah, also with the stem and leaf plot. So here, if I was to do that here, that can be represented as a dot plot as well.
But you're losing some of the data. You can get something back out of the stem leaf plot back into the originals, but in this you don't know where they are.
Right. Well, you see, with this 150, there are 4 dots here. So if you look here, 150 is listed 4 times in this data set. So pretty much you can see 150 is there 4 times. $100 here, that's there 3 times. Okay. And this dot right here is probably 70 because this one is 60. They're close to each other. Okay. So it's pretty much just an illustration of how a dot plot can be used. Okay. All right. So here, in this particular dot plot that we have, let's say we want to use that dot plot to determine the mean, median, and mode of the data represented by that dot plot. Okay. And what I'm going to do here is go ahead and draw what I have. Use blue here. That is at 2. So let me stop sharing here so you can see this here. I don't know if that's going to help you up there, but all right. Here we want the mean, the median, and the mode. Okay. Well, right off the top, what's the mode?
9.
It's 9, because that's the most frequent data value. Because see, 4 dots that are above the number 9. Okay. And then we can go ahead and find the mean and the median. Let's see. The mean is just the sum of all the data values divided by how many data values we have here. Okay. In this case here, there's only 1, 2, plus, well, this is halfway between 2 and 4, so that has to be 3. This 4 has 3 dots. So I'm going to say 4 times 3. The 5 only has 1 dot there, so there's 5 there. The 7 has 2 dots. So this will be 7 times 2. And that 9, as you can see, has 4 dots. Now, how many dots are there in the 12? So we have to divide by 12. Okay. And here we'll need some room for this. And we already said the mode was 9. Okay. So let's just simplify what's on top, the numerator. Let's see, 2 plus 3, and then 4 times 3, that's 12, plus 5, plus 7 times 2, that's 14, plus 9 times 4, That's 36. And that whole thing is divided by 12. So if we were to add all those numbers in the numerator, what would we get for a sum?
72.
That'd be 72. And what's 72 divided by 12?
6.
That'd be 6. So the mean of this data set would be 6. And now for the median. I already know we got 12 data values. So that means we need to look at, in this case, the two middle numbers. In this case, the 6 and the 7.
5 and 7.
So the 1, 2, that's 5. And this next one, 7. So 5 plus 7, well, divide by 2, not 12. So 5 plus 7 is 12. 12 divided by 2 is 6. So the median is also 6. Okay. And of course, that's the most frequent data value that is 9. Okay. So that's how we found the mean, the median, and the mode of this data set. Okay. Any questions on this? Okay. Okay. Next, we're going to look at measures of variation, or what they call measures of variability. That's how the data values vary or how they spread. Okay. Now, variability can be visualized by using what they call a histogram or a stem plot or the dot plot that we just used. Okay, so here variability can be measured by using what they call the range, the mean absolute deviation, the minimum and maximum usual values, and of course the interquartile range and percentiles. Now, the interquartile range and percentiles we'll talk about in section 8.3. Okay. Now, the definition of the range is the distance between the highest value and the lowest value. And it always has the same units as the data. Okay, so if our data set is in feet, the range of that data would be in feet, or in dollar signs, or in money amounts, then the range will be in dollars. So if we had these measurements like 43, 42, 23, 63, 12, 34, and 58 meters, in this case, these measurements will have a range of 51 meters. That means the largest data value you see here is 63. The smallest data value we have is 12. So if we subtract 12 from 63, you'll get 51 meters. Okay, so that's how we calculate the range of any data set. Okay. Now the deviation of x from the mean, which is of course notated by x bar, is that number x minus x bar. Okay, you just take each individual data value, subtract from it whatever the mean is. That would give you what they call the deviation. Now the absolute deviation is going to be this. It'll be x minus x bar, but you have to take its absolute value. If you recall, absolute value is always going to be a positive number. And absolute value means the distance that number is from 0 on a number line. So that's why we use absolute value. It's always positive. All right, now on the next slide. Let's say the data was 1, 5, and 6. The mean would be 4, so that means you have to add 1, 5, and 6 together. That would give you 12. 12 divided by 3 would be 4. Okay. So for the data value 1, if we want its deviation, we have to do 1 minus the mean. So it'd be 1 minus 4, which would give you this -3. And then for the absolute deviation, you just take the absolute value of -3, which is 3. Okay. Questions on that? Okay. Oops. Never mind. Okay. All right. Let's talk about the mean absolute deviation. I don't know where that A is equal to pi is where it came from, but I'll have to fix that because I had to edit this slide and the next slide because the slides that I gave you on Blackboard, 2 of them are just incorrect when they had those subscripts for X1, X2, and X3. All right, we're going to talk about this here. Let's say the data X1, X2, and X3 do have a mean called X bar. If we were to take the sum of their deviations like this, X1 minus X bar, and then X2 minus X bar, and then X3 minus X bar, and add them together. That would seem like a measure of spread or variation of data. But if you were to add each of those individual deviations together, you can get a sum of 0. Okay, and this is the reason why. So starting at the bottom of this slide, if I was to add these individual deviations together and kind of use what they call the commutative property, meaning put the order here like X1, X2, and X3 grouped together, and then that'll be minus 3 times X bar, because notice you got a minus X bar, another minus X bar, and another minus X bar. You have 3 of them. So it's -3 X bar. And then on the next slide, you'll see this. The X bar, which is the mean of those 3 data values, that's this expression right here, X1 plus X2 plus X3, all divided by 3. And here they use some algebra by dividing out the 3's to get this. And if you were to add those 2 together, you'll get a sum of 0. And I know that might have been their way of doing it, but let me show you how I would do this. Well, it would be done with numbers. Now I'm going to take those numbers 1, 5, and 6. Okay. So here the mean was, and that's divided by 3. So 12 divided by 3, that gives us 4. So if we were to find the deviations for each one of these, for X equal 1, that would be 1 minus X bar, that's 4, which is -3. And then for 5, that would be 5 minus 4, which is 1. And then for 6, that'd be 6 minus 4, which is 2. Now, if you just took the sum of these, you would get 0. Okay. And that's always going to be the case for any data set. Okay. So that's why it's like that. So one way to measure the spread of the data is to take the sum of their absolute deviations from X bar and then divide by 3 in order to obtain the mean of the absolute deviations. Okay, so on this next slide, we call this MAD, or the mean absolute deviation. I know. So it's the absolute value of X1 minus X bar, plus the absolute value of X2 minus X bar, plus the absolute value of X3 minus X bar. Okay. The MAD tells us how much each score, on average, deviates from the mean.
So taking the example you have with Word, what would that work out to?
Okay, let's look at it. All right, in this case here, if I want the mean absolute deviation, and in fact, I can use this table right here and extend this out to this. Absolute value of X minus X bar, since I already found out what X minus X bar is. So for 1, I came up with -3 for the deviation. If I take this absolute deviation or the absolute value of -3, it's going to end up being 3. And then for 5, I came up with the deviation of 1, absolute value of 1. Well, that's easy. That's just going to be 1. And then for 6, I came up with the deviation of 2. Absolute value of 2 is 2. So now if I want its MAD, or the mean absolute deviation, I just take the sum of these numbers and divide by 3. That's 6 divided by 2, by 3, which is 2. So the mean absolute deviation would be 2. Okay. Questions on that one? Okay.
When you say absolute deviation, is when you put those little bar things?
Yes.
Okay.
And the word absolute means absolute value.
Okay.
And of course, the mean, you have to take the average. Any other questions? Okay, so such a problem like this one. Mr. Lin grew 250 tomato plants. After the first week, he selected 4 tomato plants and measured the height, 5, 6, 3, and 10 centimeters. And here we want to calculate the mean absolute deviation of the heights, or MAD. So the first thing you have to do there is find out what the mean is. You have to add 5, 6, 3, and 10 together and divide by 4. Well, 5 plus 6 plus 3 plus 10, that's 24. 24 divided by 4 is 6. So the mean absolute deviation there would be 6.
So tomato plants are about 6 centimeters tall.
Yeah.
In general.
Mhm. All right, now, for the mean absolute deviation, here they took each data value minus the mean. So for 5, that's 5 minus 6, and then take the absolute value. Then 6 minus 6, which says take the absolute value of that. Then 3 minus 6, you take the absolute value of that. And then 10 minus 6, take the absolute value of that. But here we got 4 data values, so we have to divide the whole thing by 4. And in this case, 5 minus 6, that's -1, so we have the absolute value of -1. 6 minus 6 is 0, so we have the absolute value of 0. 3 minus 6 is -3, so we have the absolute value of -3. And then 10 minus 6, that should be 4. I don't know where they get -4 from. It's 10 minus 6, that's 4.
Yeah, 6 of like half dozen the other, so absolute value.
Mhm. So yeah, take the absolute value of 4. It's probably not going to matter, because on the next slide, you'll see that it's going to end up being 4. Okay, absolute value of -1 is 1. Absolute value of 0 is 0. Absolute value of -3 is 3. And then absolute value of 4 is 4. So 1 plus 0 plus 3 plus 4, that should give you 8. 8 divided by 4 is 2. So to answer that question, the mean absolute deviation is 2 centimeters, which is a representation of the spread of the heights.
Would an appropriate word to describe that in answering back be the tomato plants are about 6 centimeters, give or take 2 centimeters? Because that's the average they are from the mean.
I don't think so. I'm not sure. Because I know with standard deviation, I know that's just that's just a data value that tells you the spread of that data. And then usual and well, maximum and minimum usual values usually give you a range.
Sorry, I look back and see if word problems at us, so I'm trying to really understand that.
Oh, okay. All right. All right. Any other questions? Okay. And that's the formula in the blue box there. So if you choose the mean as your measure center, then you could choose the mean absolute deviation as your measure of variation. Okay. Now this extends for n number of values here. So you want to be careful of that because n is going to be the number of data values here. These sums are going to depend upon how many you have. Those absolute values of the data value minus the mean. Okay. So let's look at problem number 17 on page 357. All right, in this case here, we want to find the mean and the mean absolute deviation of the data. And we'll round the final answer to one additional decimal place than the data itself. So in this case here in part A, we got 3, 5, 2, 11, and 3. 3, 5, 2, 11, and 3. Okay, does everyone have this? Okay, let me just stop sharing here so that way y'all can. All right, the first thing we have to do there is find the mean of this data set. And I should say X bar. So to find the mean, we just add those 5 numbers. Pretty much get how many data values they are. You divide by 5. So what's 3 plus 5 plus 2 plus 11 plus 3? 24. And 24 divided by 5 is how much? 4.8. So the mean of this data set is 4.8. All right, and now we want to find the mean absolute deviation of the data. Now this is what I would do. I'll put a table here. The X will be each of these individual data values. 3, 5, 2, 11, and 3. The next column would be X minus X bar, as I'll subtract each data value minus the mean. Then the next column would be the absolute value of each of those deviations. That's the absolute value of X minus X bar. Okay. So for 3, what would 3 minus 4.8 be? Negative 1.8. And then the absolute value of that would be 1.8. And now for 5, what's 5 minus 4.8? 0.2. And its absolute value would be 0.2. And now for 2, 2 minus 4.8. Okay, negative 2.8. And the absolute value of that would be 2.8. And now for 11, what's 11 minus 4.8? 6.2. And then the absolute value is 6.2. That's still 6.2. And for 3, well, we already figured that out. That's negative 1.8 for X minus X bar, and its absolute value is 1.8. Okay. And now for the mean absolute deviation. Here we take the sum of these numbers here. That's the 1.8 plus 0.2 plus 2.8 plus 6.2 plus 1.8. Those 5 numbers will be divided by 5. Okay, if you add these numbers up, this is 12.8. And 12.8 divided by 5 is how much?
2.56.
Okay, 2.56. Okay. Because a data set is a whole number, so that means we need to round to 1 additional decimal place. That means we need to round this up to 1 decimal place. So, one number after the decimal point. So it'd be 2.6 approximately. Okay. All right, any questions on part A? Okay. And And does everyone still see some people writing this down? All right, now in part B, we have each of those data values to one decimal place. Well, one decimal place, so that means it's got to be the 2 decimal places when we give our answer. Think that I have to erase all this. All right, so here we got 4.1, 7.1, 12.1, 5.1, and 2.1. First of all, we need to find the mean, and I'm just going to label this as X bar. So we add 4.1, 7.1, 12.1, 5.1, and 2.1. Oh, that's divided by 5. So what's the sum of 4.1, 7.1, 12.1, 5.1, and 2.1? 30.5. And 30.5 divided by 5 is 6.1.
You're right.
Yeah. So the mean there will be 6.1. Now, here's how we find the mean absolute deviation. Each X value, I'm going to list those in the column. 12.1, 5.1, 2.1. And then we got X minus X bar, and then the absolute value of X minus X bar. All right, so for 4.1, what's 4.1 minus 6.1? Negative, just negative 2. And then the absolute value of negative 2. And now for 7.1, 7.1 minus 6.1 is how much? That'd be 1. And then the absolute value of 1. And now for 12.1, 12.1 minus 6.1 is what? 6. Absolute value of 6. And then 5.1, 5.1 minus 6.1 is how much? Negative 1. Absolute value of negative 1. And then 2.1 minus 6.1. Negative 4. Absolute value negative 4. Okay. Now, if you were to take the sum of this column that's in the middle, you're going to find out that this will always be equal to 0. Okay. Now, for the mean absolute deviation, you take the sum of these numbers, divide by 5. So 2 plus 1 plus 6 plus 1 plus 4 is how much? 14. 14 divided by 5. 2.8.
You have to have 0.
Yeah.
Why do you have 0?
Because the problem, it does say round to one additional decimal place than the data set. So if I was going to say 6.1, well, if they want that, then they probably don't want that 0 there. So for the mean, it'll be 6.10, and then for the mean absolute deviation would be 2.82. All right, any questions about finding a mean and a mean absolute deviation? Okay. All right, let me skip this slide here. We're going to talk about minimum usual value and maximum usual value. Here we can use the mean absolute deviation to determine an interval of usual values. And an interval is just going to be a range of numbers. Because you're going to have the minimum usual value and the maximum usual value. That would give you a range of usual values here. Okay. If we let X bar and the MAD represent the mean and the mean absolute deviation of a collection of numbers. Usual values of the data belonging to this interval would be this: X minus 2.5 times the mean absolute deviation and X bar plus 2.5 times the mean absolute deviation. Where, in this case, the minimum usual value is going to be this: X bar minus 2.5 times the mean absolute deviation. The maximum is going to be X bar plus 2.5 times the mean absolute deviation.
Where are we getting 2.5?
That's what they're using. Now I'm going to tell you this. I teach statistics. We wouldn't be using mean absolute deviation, we'd be using standard deviation for finding the minimum and the maximum usual value. The minimum usual value would be something like X bar minus 2 times the standard deviation. And the maximum would be the mean plus twice the standard deviation. Okay. So your guess is as good as mine where they got 2.5 from. Okay. That's statistics for you. But in this case, we're going to use 2.5 times the mean absolute deviation and subtract from the mean to get the minimum, add to the mean to get the maximum. Okay. A value called X would be considered unusual if that particular data value falls on the outside of those of that interval. If it's below the minimum usual value or if it's above the maximum usual value, that means that data value is unusual. If the data value falls in between those two, then it is usual. Okay. All right, so let me go to this example. I'm going to have to skip through these slides here. Like this one. Automakers are introducing gasoline electric hybrid vehicles to improve fuel economy and reduce emissions. According to the label, for a hybrid pickup truck, the city fuel mileage is between 20 and 28 miles per gallon. And we're going to assume that they are the minimum and maximum usual values respectively. The minimum is 20 and the maximum is 28. And here they want you to estimate the mean fuel efficiency for city driving. And then part B, they want you to estimate the mean absolute deviation. Okay. Now, we already talked about measures of center. That means the mean is going to be the midpoint or the center of all of your numbers that are in that data set. So if we're talking about the mileage between 20 and 28 miles per gallon, that means that the mean has to be in the middle. So to find that midpoint, we add the minimum and the maximum, that's 20 and 28, that will give you 48, and divide that by 2. And that will give you 24. So that means that the mean is estimated to be 24 miles per gallon.
And that expresses the average miles per gallon.
Yes, yes. That's what that means. Any other questions? Okay, so that's part A. Now here's part B. And that's what that is. The mean fuel efficiency for city driving for this car is approximately 24 miles per gallon. Now in part B, they're using that formula that's in that orange box, where in this case, the maximum usual value was the mean plus 2.5 times the mean absolute deviation. And here the mean, the maximum usual value was 28. Okay, because if you remember that interval from 20 to 28, the 28 was the maximum usual value. So that taking 28, and that's going to be approximately equal to the mean of x bar plus 2.5 times the mean absolute deviation. They're using this to find what the mean absolute deviation is going to be. And the mean we came up with was 24, so that's 28. It's approximately equal to 24 plus 2.5 times the mean absolute deviation. Here they're using a little bit of algebra to get the mean absolute deviation by itself. What they did here was subtracted 24 on both sides. They didn't show that here, but they subtracted 24 on both sides. That's going to be 4 is equal to 2.5 times the mean absolute deviation. And to get the mean absolute deviation, we're multiplying it by 2.5, so we need to divide by 2.5 to get 1.6. So 1.6 is approximately the mean absolute deviation.
I asked what that means in perspective of the original problem.
Okay.
And what does that mean about the car itself? What is it expressing?
Good question. Okay. Well, deviation is just the spread of the data, so that means the spread of the fuel efficiency for the various, for that particular type of car would probably be about 1.6 miles per gallon. Okay. That's probably the best way that I can explain it, since the word deviation has to be spread, that entire data. So that spread would be about 1.6 miles per gallon on average. All right, any other questions? Okay. The one that I wanted to do that dealt with finding the minimum and the maximum usual value and determining whether it is, each data value is usual or unusual would be something like this one. The teacher gives a test for which the average is 72.8 and the mean absolute deviation is 4.7. Assume the histogram for the test scores is approximately bell-shaped. So in part A, we want to ask this question: where the score is 65 be usual or unusual? So I'm gonna write down the mean, which was 72.8. The mean absolute deviation, that's 4.7. And we want to know the score 65 is going to be usual or unusual. So we'll start with that. All right, in this case here, let's start by finding the minimum usual value. And of course, to find the minimum usual value, that's going to be the mean minus 2.5 times the mean absolute deviation. Okay, so basically, the mean there is 72.8 minus 2.5 times the mean absolute deviation. That's 4.7. And this, you should be able to type directly in the calculator depending upon which one you're using. So if you do 72.8 minus 2.5 times 4.7, okay, that's your minimum usual value, that's 61.05. And now for the maximum usual value. We do x bar plus 2.5 times the mean absolute deviation. Okay, right. Because this is the same, these are the same numbers, but here you're just going to have a plus sign in between. So when you do 72.8 plus 2.5 times 4.7, you'll get 84.55. Okay. So this is what we call the range of usual values. And it's going to range from 61.05 to 84.55. So to put that in perspective, this teacher's test scores for her students range from 61.05 to 84.55. So now in part A, would a score of 65 be usual or unusual? Is usual. So the answer part A, 65 is usual because 65 falls between 61.05 and 84.55. Now, what about a score of 87? Would that be usual or unusual? This is unusual because 87 is bigger than the maximum usual value of 84.55. All right. Any questions about finding the minimum and the maximum usual values and determining whether a data set or data value is usual or unusual? Okay. All right, and let me get to this final slide here for this section. Here we go. This was similar to the one that I just did not too long ago. The teacher announces that most scores on the test were from 40 to 85. Assume they are the minimum and maximum usual values. So here the minimum is, is 40, the maximum is 85. Here we want to find the mean of the scores, that's part A, and the mean absolute deviation of the scores. So this is from 40 to 85. Here. And let's say we want to find the mean of the scores. This is part A.
The mean of the scores is not the same number as the mean that was used to create the numbers to begin with.
Right. Okay, because all we have here is just a minimum and the maximum.
You don't have enough data to work with.
You don't have anything, any data set to work with. So the way we do that here, we just have to add the minimum and the maximum value together and divide by 2. Because that's all we have to work with here. 40 and 85 would be 125, and divide 125 by 2 and you'll get 62.5. So that's the mean of this data set. Okay, now part B, they want the mean absolute deviation. Now, I think in the example that I showed you, they use the minimum usual value. And that's equal to X bar minus 2.5 times the mean absolute deviation. So we need to find out what that mean absolute deviation is. All right, we know what the minimum usual value here, that's 40. That's given to us right there. And that's equal to X bar, well, we just found out what X bar is, that's at 62.5. So let's substitute that. And then that's minus 2.5 times MAD, the mean absolute deviation. Okay. So this is one of those equations where you have to get the mean absolute deviation by itself, MAD, just like solving an equation with a variable in it. All right, let's move the 62.5 over where the 40 is by subtracting 62.5 on both sides. So what's 40 minus 62.5? Negative 22.5. That's equal to the negative 2.5 times the mean absolute deviation. And to get this variable, the mean absolute deviation by itself, we're multiplying by negative 2.5. So let's divide both sides by negative 2.5. So that means the mean absolute deviation will have to be 9. Okay. So the mean absolute deviation for this would be 9 based on that. Okay. Does anybody have any questions about section 8.2? Okay. Now, I realize it took me a couple of days to cover that particular section, but there you have it. So, the homework will be available on WebAssign for you to complete. And Wednesday, we'll talk about percentiles and box plots and outliers. Okay. And make sure your name is on that sign-in sheet. I forgot to bring my own, but make sure that you print your name on the sign-in sheet so that way I can mark you present. And I'll see you Wednesday.
Thank you.
All right.